Okay, quiz 8.1 deals with intermolecular forces and some of the basic properties of gases. We look at question 1. This asks to state the strongest intermolecular force exhibited by each molecule. So that first one, CH3COOH, has a carbon, hydrogen, 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 carbon, oxygen, oxygen, hydrogen. That condensed structural notation is perhaps a bit confusing at first, but that's the molecule. And we see here we've got a lone pair on an oxygen and a hydrogen attached to an oxygen. And so this molecule is capable of hydrogen bonding. The next molecule, let me erase this. And some of these I'll go through rather quickly. Ozone, because all of the atoms in this molecule are oxygen, we know there are no polar bonds. There's no opportunity for hydrogen bonding. And so London dispersion forces are the only types for ozone. NO2, you'd have to draw out the Lewis structure. To be sure of this, but nitrogen-oxygen bonds are weakly polar, and because of this lone pair, there is not symmetry to the molecule that would cancel out those polar bonds. So this is a polar molecule, and dipole-dipole interactions are going to dominate for the nitrogen dioxide molecule. Okay, next we have C3H8. Now, however I draw this out, there will be no polar bonds, and there will be no opportunities for hydrogen bonding. And so this is propane, and it also exhibits only London dispersion forces. CH3OH. Is a methanol molecule, and again we've got a lone pair on an oxygen, we've got a hydrogen bonded to an oxygen, and so hydrogen bonding is what methanol will exhibit. Okay, CH2F2 has a tetrahedral molecular geometry, but these carbon-fluorine bonds will be highly polar, while the carbon-hydrogen bonds are not. And so this molecule will have a net molecular dipole. So dipole-dipole interactions will be exhibited. And then the last one, I'll just put over here, nitrogen gas, completely non-polar, and so London dispersion forces. Hold on a sec. Scroll down to question 2. Which substance in each pair of these would have the highest melting point and boiling point? And this is just another way of saying which has the strongest intermolecular forces. Between krypton and neon, krypton is a larger atom than neon. They're both noble gases, but krypton's further down in the periodic table. So krypton would have the higher melting and boiling point due to its atomic size. Looking at NO2 and N2O4, you see they have the same composition, the same types of dipole strengths between nitrogen and oxygen bonds. But N2O4 is twice as massive. It has twice as many atoms. So N2O4 will have the higher melting and boiling point. Oxygen and nitrogen, it will be down to either the atom size or the molecular weight. You could frame it either way. The oxygen atoms are more highly polarizable, and so they'll exhibit stronger dipole-dipole forces, and then O2 is 32 grams per mole, N2 is 28 grams per mole, so it's also a more massive molecule. Now looking at this next pair, if you were to count up all of the carbons and all of the hydrogens in both of those instances, you'd see that they're exactly the same. They are both C4H10. That's a butane. One of them is all in a line, and the other one you can see is highly branched with 3 carbons bonded all to a central carbon. So in this case, the atoms are the same, the molar mass is the same, but their shape is a little bit different. And the straight chain molecule is going to be presenting a larger surface area to its neighbors, and so it will have at least a moderately higher melting point and boiling point. And then lastly, C6H14, that's hexane, versus C8H18, that's octane. The octane has a higher molar mass, it has more atoms, so it will have a higher boiling point. Let's move on to question 3. So question 3 says to draw and describe the 2 features that a substance must have to be capable of forming hydrogen bonds. So you must have a region of the molecule capable of functioning as a hydrogen donor, and that is a hydrogen bonded to a highly electronegative atom like oxygen, nitrogen, or fluorine. And then you also need to have a hydrogen acceptor. And that is going to be a lone pair, again located on oxygen, nitrogen, or a fluorine. Any molecule which has both of these features will be capable of hydrogen bonding. For question 4, list the 5 postulates of the kinetic molecular theory of gases. I'll just say them rather than spend 10 minutes writing them out on the board. The first postulate is that gas particles are in constant random motion. The second postulate is that gases are composed mostly of empty space. You could also say this as the volume occupied by the molecules is negligibly small compared to the volume occupied by the gas sample. Third is that these gas particles have no attractive or repulsive forces. Fourth is that collisions are elastic, and remember that's a physics term, says that kinetic energy as well as momentum is conserved in any collision. And the best way to think about it is that they bounce off each other at the angles and velocities that you would predict for something hard and rigid like a billiard ball. And then 5, the last postulate of the kinetic molecular theory of gases, is that the average kinetic energy of gas particles is proportional to the temperature. So if I double the temperature, I've doubled the average kinetic energy of these particles. Then we have some unit conversions. Pressure is the one sort of measurement that even in our chemistry class we kind of deal with a lot of different types of units. You know, people out in the real world will use pounds and even stone or other maybe local measuring units, but scientists all around the world care about the gram and the kilogram and their derivatives like the microgram or the milligram or the megagram, right? It's all based on the gram. But scientists around the world still can't quite agree on units of pressure, and so we need to be familiar with atmospheres, with millimeters of mercury, and with torr, those 3 units. And honestly, if you were to go on in chemistry, you'd have to become familiar with the bar as well, at least, and perhaps even the Pascal. It's kind of a mess. So luckily, we know that 1 millimeter of mercury is equal to 1 torr. They're actually identical in their magnitude. And then 760 torr is equal to 1 atmosphere. And so 760 millimeters of mercury are also equal to 1 atmosphere. So let's do these conversions. I'm sorry, there's the 5 postulates of the kinetic molecular theory. Here we're going to complete, that should have said convert the following pressures into atmosphere. That's a typo, but that's all right. So 224 millimeters of mercury. 224 millimeters of mercury. And we know that 760 millimeters of mercury is 1 atmosphere. And so, put that in your calculator and you'll see that it's 0.295 atmospheres. 0.295 atmospheres. And then 65 millitorr. So that milli is hopefully not going to present too much trouble. 65 millitorr. And I know that 1,000 millitorr is 1 torr. And then that 760 torr is 1 atmosphere. So put that in your calculator. It's going to be a very small pressure. That'll be 8.6 times 10 to the negative 5th atmospheres. And I'm not sure how that value compares to things like, say, the pressure of interstellar space, or anything like that, but it's a very low pressure. Certainly we can get lower than 65 millitorr in the laboratory with relative ease, but it would require laboratory equipment. You know, your vacuum cleaner, for example, is not pulling a vacuum anywhere remotely close to this. It's a pretty low pressure. Okay, and then just to practice going the other direction, 1.25 atmospheres to torr, 1.25 ATM, and 1 ATM, 760 torr. So this is going to be 950 torr. Although because we have 3 sig figs here, I'm going to write that as 9.50 times 10 squared torr. That's just using scientific notation to force that to be significant. Which I guess also brings up the point that this conversion, 760 torr to 1 atmosphere, I'm not sure if that's a defined exact conversion, but it's at least good to more sig figs than it would appear. So just treat this conversion as if it's never going to limit your sig figs. It's at least 3 or 4 sig figs, and it might even be a perfectly defined conversion that gives you infinite sig figs, kind of like, well, there are a couple like the conversion between inches and centimeters, or say something like grams to kilograms itself. Anyway, okay, so that is quiz 8.1.